Good day, students. Welcome to part one on our definite integration by substitution. Before we get started with the examples, let's go ahead and write down the formula that will guide our problem solving process. Okay, so formula. So if you have a definite integral from a to b of a unique type of function, the function is a composed function f of g of x multiplied by the derivative of the inner function g prime of x dx. This can be written as, using substitution, the integral from u of a to u of b of f of u du. Okay, this happens where u is equal to g of x and du is some integer multiple of g prime of x dx. Okay? Now, how do you know when to use integration by substitution? Is in a situation where you have a composite function and the innermost function has a derivative being multiplied by dx as a second function. All right? One thing you want to note when you're doing definite integration by substitution is that the limits of integration do change. Okay, if it's in an indefinite integral situation, you don't have to bother with that because you don't have limits. When you have limits and you're making use substitution, note that the limits of integration do change. Okay, this is the x value here, and this is in terms of u, so we have to evaluate u at the lower limit and at the upper limit of our x values here. Okay, so keep that in mind. Let's write that. So note, limits of integration change. Okay, limits of integration do change. They do change when you're evaluating integrals using u substitution. All right, let's take a look at the first example. We're going to evaluate the definite integral from 1 to 2 of 1 over the quantity 2 minus 3x squared dx. All right, let's take a look at this problem. Can we evaluate this using substitution? Absolutely. Let's see if we can express this integral as a composite function times the derivative of the innermost function, a multiple of the derivative of the innermost function. All right. So let's see if I can separate this here. This is a composition of multiple functions. We have a rational function, a square function, and then a linear function. But the linear function is the innermost one. Okay. So let's see. How about we write this problem like this: the integral from 1 to 2 of 1 over 2 minus 3x squared. Now, since there's no number here, I'll just write 1 times dx. Okay. Now we're going to do a real quick test to see if we can get a multiple of 1 dx after differentiating the innermost function, which is 2 minus 3x. All right, so let's extract the innermost function, 2 minus 3x. Let's see what we have here. So this is just a test. We have 2 minus 3x. If we differentiate this, what do we get? Using differentials, this is going to be negative 3, because this derivative of this is 0, negative 3 dx. So if we multiply this by negative 1/3, we'll end up with this. So this is perfect because this is a multiple of this second function right here. All right, so we can use u substitution. All right, so let's go ahead and do it. First of all, we're going to pick our u. Our u is the innermost function, which is 2 minus 3x. All right, we're going to differentiate using differentials. So du, derivative of this is just 1 times du, equals the derivative of 2 is 0. Derivative of this is negative 3 dx. Okay, But this is 1 dx. All right, or I can just look at this as just dx. I need dx by itself. So in order to accomplish that, I'll have to divide both sides by -3. Okay, so I can have a nice and neat substitution. So du over 3, negative du over 3 is equal to dx. Okay, now I know how to make my substitution with my u. Now how about my limits of integration? Remember we indicated here that you have to note that the limits of integration do change. So what happens when x is equal to, let's do the upper limit, when x is equal to 2? Well, that simply means 2 gets substituted here. So u is going to be 2 minus 3 times 2. And if you do the calculations, you have 6 minus 2, negative 6 plus 2, which is -4. And then at the lower limit, when x is equal to 1, what happens? Well, we'll just simply plug in 1 into this u substitution equation here. So u is going to be equal to 2 minus 3 times 1, which gives us -1. Okay? All right, so we're going to make use of this. Let me just show you what I'm going to make use of. This u right here, this, and these limits in my new integral. Okay, my new definite integral. So let's go ahead and rewrite it. So we're now going to have the integral from -1 all the way to -4 of, let's see, 1 over, now instead of this entire 2 minus 3x squared, it's simply going to be u squared. Now, dx, or 1 dx, is the same as this. We just replace that with negative du over 3. Okay? So this is what it's going to look like. All right, let's go ahead and write this in a way that's easy on the eyes to evaluate. I'm going to factor out the constants using the constant multiple rule. Factor out -1/3. -1/3. And I want to apply the power rule here, but this form is not easy to express, to apply the power rule for integration. So how about I write this as u to the -2 du. Okay, I'll take a look at this expression, and this one, which one is easier to evaluate. You notice that this is much easier to evaluate because it's written in a form that's easy to apply the rules. So rewriting definitely makes the process of integration easy. Okay, now let's apply the power rule here. So we're going to have 1/3 and also FTC part 2 times u to the, we're going to add 1 to the power. We'll add 1 to -2. You end up with -1, and whatever you get, you put that downstairs too, like that. And this is being evaluated from -1 to -4. Okay. Now we're going to use FTC part 2, which involves evaluating the antiderivative at the limits of integration. So we're going to have 1/3 times, let's see. Now another thing we can do, you see this negative right here? We can factor that out. So let's put the minus here. And then we're going to have -4 to the -1 minus minus -1 to the -1. Okay, you have to remember that you always plug in your the upper limit of integration first before the lower limit of integration, and you end up with an expression like this. Okay, all right. Just a quick thing to note: there was a minus here before, right? So this minus, we bring it over here. And then when I factored out this minus to here, so this becomes a plus. Okay, so let's keep track of our minuses. So this minus, 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 if we take this out, that makes this a plus. All right, excellent. So let's go ahead and finish this off. We'll have 1/3 times, we find the reciprocal property of exponents. This is -1/4. And then this becomes -1. Times this 1 becomes +1. All right. Okay, so now we have 1/3 times negative 1 over 4 plus, if you find the LCD, put this over 1 times 4, top and bottom, 4 over 4 equals 1/3 times 3 over 4, and then you multiply, and your final answer is 1/4. Okay, so that's that. All right, let's take a look at question number 2. For number 2, we're going to evaluate the definite integral from -1 to 2 of 3 to the x root 1 plus 3x, 3 to the x dx. Okay? All right, so let's see. Can I apply use substitution to this problem? Do we have a composite function with a inner function being expressed as having its derivative expressed as a multiple of the second function? Let's rewrite this to see if we can find that. So we can write this as an integral from -1 to 2 of the square root of 1 plus 3x to the x. This is a composite function right here. We're composing the radical function for the linear function and an exponential function. Okay, so this is the innermost function here. Now, and then over there we have 3 to the x dx. Now the question is, if I differentiate this inner function, do I end up with a multiple of this function right here? So let's do our test real quick to see if I can use integration by substitution. So test on the side, let's take the innermost function, and let me differentiate it using differentials. Okay, so if I differentiate this, this is going to be 3 to the x times the natural logarithm of the base 3, okay, dx. Now let's take a look at these two. This is perfect because this right here is a constant. We can look at this ln 3 times 3 to the x dx. So what we have is a multiple of 3 to the x. We're multiplying ln of 3 times 3 to the x dx. So note this is a constant, okay? So since the derivative of an innermost function, if you differentiate it, you have a multiple of the second function right here, dx. That means we can use substitution. All right, so let's go ahead and do it. So we're going to call u our innermost function, which is 1 plus 3 to the x, and then differentiate both sides using differentials. Okay, so du, derivative of u is just 1 du, equals derivative of 1 is 0 plus the derivative of 3 to the x is 3 to the x ln 3. Okay, let me just go over the differentiation rules. Remember, d dx of a to the x is a to the x ln a. All right, that's the rule I'm using here. Okay, so we have that, but we have to express it as differentials, dx. Here we have 3 to the x dx. If I want to make a nice substitution, I need to have 3 to the x dx by itself here. Okay, so how do we accomplish that? We simply divide both sides by the natural logarithm of 3 to eliminate that constant. All right, so we're going to have du over the natural logarithm of 3 equals 3 to the x dx. All right, so we know how we're going to substitute this innermost function with a u. We know how we're going to substitute this with du over ln 3. Is that all we need to care about? The answer is no. Remember, the limits must change. Okay, anytime you're doing u substitution with definite integrals, it must change the limits. So upper limit when x is 2, what does that mean for u? Well, that means that u is going to be 1 plus 3 to the second power. We're evaluating u at x equals 2. Okay, so just plug in 2 here. So if you do the math, 3 squared is 9 plus 1 is 10. Okay, and then when x is the lower limit, -1, this is going to be u is going to be u of -1, right? I should have written u of 2 here, but that's okay. So u of -1, plug in -1, the lower limit, into u. You're going to have 1 plus 3 to the -1. So you're going to have 1 plus, applying the reciprocal property of exponents here, this is 1/3. And if you find the LCD, 3/3 plus 1/3, 4/3. So these are your limits of integration. All right. So my new integral, I'm going to be making use of this substitution, this right here, the upper limit and the lower limit. All right. Okay, so let's write our new integral. So our new integral is going to become the integral from 4/3 to 10 of the square root of u, replace 1 plus 3 to the x with u, okay? 3 to the x dx, we'll replace it with du over the natural logarithm of 3, all right? This looks like a mess to integrate, right? So let's see how we can rewrite it so it's easy on the eyes. So how about I factor out this constant? I'll have 1 over the natural logarithm of 3. Integral from 4/3 to 10. How about I express this as u to the 1/2 using the nth root property of exponents? Now, in this form, I can easily apply the power rule, okay? Let's go ahead and do that. This is going to become 1 over ln natural logarithm of 3. Applying the power rule to the integrand, we're going to have u to the, if you add 1 to 1/2 is 3/2, so 3/2. Whatever power you get, you apply that to the denominator, so it becomes 3/2. Evaluated from 4/3 all the way to 10. Okay? Alright, now before I apply FTC part 2, I can factor out this 3/2 right here so that I don't have to keep writing that over and over again. It just complicates the whole process. So why don't we just go ahead and factor it out? If I factor it out, I'm going to be multiplying this by the reciprocal of this denominator fraction right here. So we're going to have 1 over natural logarithm of 3 times 2/3. Okay, now let's apply FTC part 2 to the numerator. So we're going to have 10. The inner function evaluated at the upper limits, 10 to the 3/2, minus u to the 3/2 evaluated at 4/2, which is going to be 4/3, raised to the 3/2. All right, so that's what you get when you apply FTC part 2. So let's do some cosmetics and make it look pretty. So this is going to become 2 over 3 times the natural logarithm of 3. And then in here we have 10 to the 3/2 is the same thing as 10, 10 root 10, okay? Minus the same story here, the numerator, we can write the numerator to the 3/2 will be 4 root 4, and then the denominator to the 3/2 will be 3 root 3. Okay, hopefully this makes sense. If you think about it, let me do this on the side real quick. So if you have 10 to the 3/2, that is the same thing as 10 to the 1 plus 3/2. I'm sorry, 1 plus 1/2. Okay, and then using the reverse of the product property of exponents, you can write this as 10 to the 1 times 10 to the 1/2, which becomes 10 root 10. Okay, so I'm just working backwards using the properties of exponents. That's how I got this piece. And then this one I used the quotient property of exponents to apply this power to the numerator and the denominator, and I ended up applying this again to both numerator and denominators to end up with this. Okay, all right, let's keep on beautifying our work here to make it look nicer. You can have a radical in the denominator, so we have to rationalize the denominator here. So we just multiply this by root 3, top and bottom. So root, see how I can put a root 3 here, and then a root 3 here, top and bottom. And also, if you note, square root of 4 is 2, right? So this becomes, let's see, what does this become? 2 over 3 times the natural logarithm of 3 times 10 root 10 minus 4 root 4 is 4 times 2, which is 8. You're going to have 8 root 3, okay? And then the denominator, root 3 times root 3 is 3 times 3 is 9. So there basically goes your final answer, all right? So that's that. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to our channel for other cool calculus clips such as this. And please post a comment to let me know what you think about this presentation. More clips can be found on math.serve.com/calculus. Thanks again for watching and have a wonderful day.